Recording is live. Okay, welcome everyone to another week of Chem 1A. Just a little review of what the forecast over the next couple of weeks look like. This week, we'll be spending time on a new topic, chemical equilibria. That's, of course, for today and Wednesday's topic. Today, on Monday, we do have a wet lab experiment. And on Wednesday, we have a dry lab based on this week's topic. This will, of course, lead us into your next exam on Monday, the 17th. That's our final module exam for the semester. And after the module exam, we'll just have a couple more topics to round out before a set of presentations. And of course, our final in, I believe, a month at this point. Our final is in about a month from now. So we're rounding the end of the semester. Hopefully, as we get towards that point of our presentations, you all have already started working on your presentations. As a reminder, of course, I do encourage you to keep track of your communications, or otherwise, for example, if you have a group chat or if you send emails, that's what I think is a good idea, simply because if on the off chance you recognize, hey, John Doe in my group isn't really participating, then when you come to me and tell me that, you can show me, hey, I've tried to make group chats with John. I've tried to reach out to him over email, and John Doe just isn't really responding or participating. Well, that's good information for me to know, especially if you have some backed up proof with it as it comes to communication. Because more often than not, some students will come and say, well, I didn't know they were trying to reach out to me. But of course, if you show me emails or messages, and I can say, well, they did try to reach out to you, it's you were the one either ignoring them or didn't even recognize that you needed to speak to them. This is all to say that with less than a month left before our presentations, you all should be in the headscape of actually trying to work on them, if not already practicing them. We have only a few more topics left for the semester. Equilibria is our last, I would say, our biggest topic of the semester that we have left. So we're in good shape for our presentations. As a reminder, next Monday, the 17th, is our exam. By this Wednesday, I'll have a draft made of the exam, and I'll be able to tell you a little bit more context behind what to expect, how it's going to be structured, as well as have a finalized reference sheet for you to refer to, so you know exactly what equations and graphs you'll have walking into the exam. Before we begin today's topic, does anyone have any questions on the forecast for this course or any other questions related to it? All right. Today, we are jumping into a brand new topic titled Chemical Equilibria. Now, flashback to a couple of weeks ago when we first talked about something like kinetics. Way back when we talked about kinetics, we had drawn a graph to represent the change in reactant and product over the course of the reaction. We knew, of course, that on the x-axis was some unit of measure of time, whether that be seconds, minutes, or hours. And of course, the y-axis was generally concentration to some degree, whether that be 1 over molarity, molarity squared, or whatever, just some concentration. Now, way back when we talked about kinetics, I gave you the graph. I told you the idea. At the very beginning of the reaction, we expect there to be high amounts of the reactants. At the very beginning of the reaction, we expect there to be very low amounts of the product. Basically, you'd be in an ideal world, it'd be perfectly zero, of course, but we're just drawing it this way on the graph to represent where we expect them to be. Over the course of the reaction, what I told you is that we expect the reactants to decrease. And over the course of the reaction, we expect the products to increase. This is what I went over those weeks ago when we went over kinetics. Way back when, this is what I told you was the expected graph of such a relationship, that by the end of the reaction, you should have, in theory, 100% product and pretty much 0% reactants. Of course, through different measures such as yield, that very rarely happens, but it's good to at least have an idea. This is not what actually happens if you were to plot this graph. In fact, if we were to replot this graph using actual real data, Although a couple things would be in common, of course, the x-axis is time, the y-axis is concentration. And at the very, very beginning of the reaction, we expect there to be high amounts of reactant. And at the very beginning of the reaction, we expect there to be low amounts of the product. So far, in line with what we'd expect. However, in reality, what happens is as the reaction progresses, it's not, in fact, a straight line for both the reactants and the products. In fact, it's more of a curve that ends up meeting. In other words, what we have been taught previously is that by the end of the reaction, we expect high amounts of product, low amounts of reactant. In truth, what actually happens more often than not is a sort of equilibrium between the reactants and products, such that they were 50-50. So the key point here is that we expect this to be a traditional downward or upward slope, a very straight line. But in truth, there's a little bit of curve to it, and the product does not get as high as we'd expect. The reactant does not get as low as we'd expect. What this leads to is what we now know, what we now describe as the concept of equilibrium. What exactly is equilibrium? Well, chemical equilibrium is established. Remember that this is a state, it's in equilibrium. Chemical equilibrium is established when the rate of formation of the products is equal to the rate of formation of reactants. This is what's referred to as a dynamic equilibrium. In essence, what's occurring when we're at equilibrium is a state of reversibility, such that we're able to say for a generic reaction, the reaction between A and B is reversible. And here we have a brand new arrow. We've actually seen this arrow before, back when we covered acids and bases. We saw it when we were identifying acid base and our conjugates. Back then, I told you, ignore what this arrow means specifically, but now we're officially introducing it. This arrow outright tells us that a reaction is reversible. In other words, it can occur in both directions. As much as A turns into B, B in reverse turns into A. This can be seen in a very simple example, such as the transformation of N2O4, dinitrogen tetroxide, to 2NO2. We should be able to recognize, based on stoichiometry alone, that the reaction is balanced. But this, in theory, should explain to you the idea behind reversibility. The N2O4 is breaking down into two NO2s, and at the same rate, the NO2 is combining back into N2O4. Now, earlier, I described chemical equilibrium as when the rate of formation of products is equal to the rate of formation of reactants. What exactly does this mean physically? Well, to understand a little bit more about equilibrium, I really like to think of a simple game of tug of war. If you've ever watched Squid Games, and you know what tug of war I'm referring to, you have teams on opposite end of the rope that are pulling the rope with as much strength as they can in order to win. Now, of course, what's happening here is if the rope is being tugged in both directions, just as the reactants are being formed to products and the products are being converted to reactants, what we have here, what can happen in a game of tug of war, is if both sides are of equal or pretty equal strength, then that rope isn't moving. We know that each team on either side is pulling that rope with as much force as they can, but the rope itself is not moving. This is an example where the rate of pull is equal on both sides. In other words, even though we know that both sides are reacting, overall, we do not see a net effect. Just like in an actual game of tug of war, if the teams are equally matched on either side. This is the basic idea behind that dynamic equilibrium. The reaction is progressing in the forward direction. It is also progressing in the reverse direction. But the point is that the rate of the forward and reverse is equal, such that we achieve equilibrium. How do we know if a reaction is at equilibrium? I mean, it's easy to just say that, oh, both sides are pulling with similar strengths or rates, and we see a net zero, the rope isn't moving. But how can we know beyond a reasonable doubt if a reaction or a system is at equilibrium? Well, the answer is simple. We calculate what's known as the reaction quotient. The reaction quotient is given the symbol QC. Q subscript C. To calculate reaction quotient, let's first look at a generic reaction. Here we have the reaction between A and B. These react to form generically D and E, where the capital letters represent the chemicals and the lowercase letters represent their stoichiometric coefficients. To calculate the reaction quotient, it is equal to the products, the concentration of which, divided by the reactants, raised to their stoichiometric values. So in the case of this A plus B, the reaction quotient is equal to the concentration of the products divided by the concentration of the reactants, each raised to the power of their stoichiometric values. So as long as we have a fully balanced equation, we can very easily calculate the reaction quotient for the reaction at hand. So for example, if we were to look back at the reaction we just went over, which was the dynamic equilibrium between N2O4 and NO2, we can calculate the reaction quotient as the product, in this case NO2, divided by the reactant, N2O4, raised to their stoichiometric coefficients. Here, the only stoichiometric value is 2 for NO2, so that is squared. Recognize that if no number is written, it is implied to be a 1 in front of the N2O4, where, of course, anything raised to the 1 is itself. So we don't need to explicitly write out the 1. So according to this, all we really need to calculate the reaction quotient is a balanced equation as well as the concentrations of the reactants and products. Things that we know at this point in this class can either be very easily calculated or determined. Now, there are a couple of useful considerations to keep in mind about this reaction quotient and equilibrium. At a given temperature, every reaction will have what's known as an equilibrium constant. So whereas the reaction quotient, QC, is the mathematical formula, every reaction will have some equilibrium constant. This equilibrium constant is known as QEQ. I'm sorry, KEQ. Sorry, there's a lot of Q's. KEQ. Some online resources or textbooks also refer to this as KC. They're interchangeable. Equilibrium constant or KEQ. I'll probably use them interchangeably depending on the context, but you might see either or. How does this help us understand if a reaction is at equilibrium? I mean, if every reaction has an equilibrium constant, we can calculate the reaction quotient. In other words, to determine if a reaction, here abbreviated as RxN, is at equilibrium, you simply compare QC to KEQ, the equilibrium constant. So KEQ is traditionally a set constant for a reaction at a specified temperature. But the reaction quotient is a value calculated based on concentrations. So if we compare the two, we'll actually have three distinct possibilities. If the calculated quotient is equal to the equilibrium constant, then the reaction is described as being at equilibrium. In other words, if QC is equal to KEQ, the reaction is described as being at equilibrium. If QC is less than KEQ, the reaction is not at equilibrium, and it will favor the products to establish equilibrium. Now, there's a little new phrase here. Favor the products. We don't know yet what exactly that means, to favor the product. But as of right now, if QC is less than KQ, it is not at equilibrium. The other option, of course, is if QC is greater than KEQ, it is again not at equilibrium and will instead favor the reactants. You see, the thing about equilibrium is that it's a state. You could describe it as a temporary permanent state. But just as how every element wants to look like a noble gas, every reaction wants to be at equilibrium. If it's at equilibrium, well, then great. Everything's fat, everything's settled, no need to worry, we're all good. But if the reaction is not at equilibrium, something will happen to get to equilibrium. What does that mean and what does that look like? Well, let's take a look at a question. Here we have the reaction, the decomposition of SO3 reacting to form sulfur dioxide and oxygen gas. I'm telling you, for the purposes of this question, the equilibrium constant is equal to 0.1. Equilibrium constant is unitless. So it's just 0.1. The question reads, at 3:50 p.m., SO3 is equal to 0.5 molar. SO2 is equal to 0.2 molar. And oxygen is equal to 0.1 molar. So at some specific time, these are the concentrations of every chemical involved in the reaction. What I'm ultimately asking you is the reaction at equilibrium? All right, well, how does this work? Well, we know that to determine if something is at equilibrium, the reaction quotient must be equal to the equilibrium constant. We know the equilibrium constant, it was told to us right here. So what we need to do right now is calculate the reaction quotient. The reaction quotient is equal to the products divided by the reactants. In this case, there's actually only one reactant, raised to the power of their stoichiometric coefficients. Recognize, of course, that there is nothing in front of O2, so it's implied to be 1, and anything raised to the 1 is itself, so we don't explicitly write the 1. SO2 and SO3 have a 2 in front of them, so they end up being squared. With that in mind, we can then plug in our values. We know that SO2 is 0.2 squared, O2 is 0.1, all over SO3, which is 0.5 squared. We're now going to plug this into our calculator. On top, we have 0.2 squared times 0.1. On the bottom, we have 0.5 squared. By plugging this into our calculator, we get 0.016. Is QC equal to the equilibrium constant? No. How can we tell? Well, look at the numbers. They don't match at all, not even with a little bit of rounding. The fact that the numbers do not match, QC is not equal to KEQ, this is what tells us in no uncertain terms the reaction is not at equilibrium. Of course, this isn't a bad thing. We're not saying something's wrong. We're simply saying that at 3:50 p.m., based on the concentrations at that time, the reaction is not at equilibrium, at least at 350. So then part B will now ask, what direction will the reaction favor? To establish equilibrium. So like I said, every reaction wants to be at equilibrium. Just like in the tug of war, they want to be in a situation where both sides are being formed at the same rate. So even though we're not at equilibrium at 350, we will eventually get to equilibrium. Maybe we've already passed it. All we know is that we need to get to equilibrium. Now, there are a couple ways to do this. Method A, which is to quite literally just refer to the rule I told you. If QC is less than, if QC is greater than, what will it favor? Well, in this case, QC is less than KEQ. Look at the numbers. That's how we know 0.01 is less than 0.1. Based on this alone, it will favor the product side. When we say favor the products, what we literally mean is that we're going to keep making more products until we hit equilibrium. That's what favor means. The reaction is not at equilibrium. That means one side is winning. To get to equilibrium, we have to make more product. We're going to favor the products to hit equilibrium. This is method A, where you would outright memorize less than, greater than, favor, or favor products or reactants. Method B is a little bit more visual. It's the method I generally prefer. What you would do, quite literally, is you would draw a line. On opposite ends of those lines, we have negative infinity and infinity. Smack dab in the center is KEQ, which we're, of course, already told is 0.1. We would then draw on this scale QC. QC is, of course, less than KEQ at approximately 0.016. By drawing the line, by drawing this illustration in this way, we're able to more clearly see visually that to get to equilibrium, we have to favor the right-hand side. And what is the right-hand side of a reaction? Those are the products. So two ways you could have identified the direction. Method A is a little bit more straight memorization of rules. If it's less than KQ, then you favor the products. No doubt about it. Method B is a little bit more visual. It's just a quick draw the scale, draw where you expect QC to be. Remember, we know it's less, so it's going to be on the left-hand side. And we can see visually that to get to KEQ, we have to favor the right. We have to go to the right-hand side of the reaction, which, of course, is the product side. So with equilibrium, with reaction quotients, not only are we able to identify if a reaction is or is not at equilibrium, we can also predict what has to be done to get to equilibrium. Do we have any questions so far? Okay. There are a few rules to using reaction quotients. The first rule is no solids or liquids are included in the calculation. The very simple reason for this is owed to their states, solid or liquid. These guys are a little bit more complicated to keep track of in equilibrium. Solids have density, liquids have weird volumes and intermolecular forces. So we don't include solids or liquids in calculations. And this isn't just specific to Chem 1A. You only really talk about solids and liquids once you get to like the upper level electives of chemistry, which I don't know if which of you plan on continuing with chemistry after Chem 2A. Is it 2A? 1B, sorry. So no solids or liquids are included in the calculation. This is a blanket rule simply because they're too complicated to really keep track of. That's only left for the upper level electives. This is only gases and aqueous species are included. Let's see what that looks like in principle. Here we have the reaction. This is the reaction between or decomposing carbon monoxide to carbon added to CO2. Oops. And I'm going to go ahead and tell you that the equilibrium constant is 7.7 times 10 to the negative 15. The question reads, at 9:02 a.m., the concentrations of the chemicals are as follows. CO is equal to 0.034 molarity, and CO2 is equal to 3.6 times 10 to the negative 14 molarity. The question simply asks, is the reaction at equilibrium and if not, which direction will be favored to establish equilibrium? So basically the same question as before. You're given a reaction, you're given concentrations. You're being asked, is it at equilibrium? And if not, just predict the direction it'll go. To do this, of course, the first thing we need to do is calculate the reaction quotient. The reaction quotient is equal to the products divided by the reactants raised to their stoichiometric values. Recognize, of course, that carbon is completely missing from this equation. Why? Because carbon is defined to us as a solid. Solids and liquids are not included in these calculations. The other way you could, of course, remind yourself of that fact is I have not given you the concentration of carbon. That should be kind of a hint in and of itself. Now we just need to plug our values in. CO2 is 3.6 times 10 to the negative 14. All over 0.034 squared. Plugging this into our calculator, 3.6 times 10 raised to the negative 14, all over 0.034 squared. We got a really, really small number. This looks to be 3.11 times 10 to the negative 11. If we compare this to the given constant, hopefully we can very quickly and immediately see these are not the same value at all. As a result, this equation is not at equilibrium. The follow-up of this says, if not, which direction will be favored to establish equilibrium? Of course, as I said, I like to use method B, the more visual tool. I'm going to draw a line. On each end, I'm going to write my infinity symbols, positive and negative. Smack dab in the center is our equilibrium constant. Our equilibrium constant is 7.7 times 10 to the negative 15. We also have QC. This is times 10 to the negative 11, which if we know our numbers, we know, of course, this is larger. Remember that we're dealing with a negative exponent. That, of course, this refers to the amount of zeros present. In the case of negative exponents, the smaller the negative means the larger the number is overall. This is what tells us, at least visually, to get to KEQ, we're going to shift to the left, aka we will favor the reactants. The left side of the reaction. So when dealing with solids or liquids, it's really just a matter of recognizing they would not be included in the equation at all. The fact that I would not give you any numbers about them, that is enough information to tell you that it shouldn't be there. And to compare the two, you simply just look at the numbers. Now, there are a couple things to know about this equilibrium constant. Number one, we've already said this, but I'll write it out explicitly. KEQ is unitless. The equilibrium constant does not, I make that very clear, does not indicate speed. What does indicate speed? That's way back in kinetics. First order, second order, all that stuff, half-life. KEQ does not directly correlate with speed. In other words, a large KEQ does not necessarily mean a fast reaction. Similarly, a small equilibrium constant does not indicate a slow reaction. It might. The reaction may have a large constant and be fast, but the two are not directly correlated. You'd have to carry out kinetics studies and equilibrium studies, and then you can comment on the two. The math behind equilibrium constant is also straightforward. If we have a reaction such as A to B, where the equilibrium constant is, say, 100, then the complete reverse reaction, starting with B, ending up with A, that KEQ is equal to the reciprocal. In this case, 1 over 100. Similarly, if we were to multiply the original equation by 2, the KEQ value would be squared. We also alluded to this when we said at a given temperature, but just so it's clear, KEQ is temperature dependent. Unless specified otherwise, you are expected to assume all of our reactions take place at room temperature. But what that means is that if I were to increase the temperature, that would technically be a different equilibrium constant. Do we have any questions so far? Okay. Let's talk about our next topic, under equilibrium. Le Chatelier's principle. Le Chatelier's principle describes or states if a system at equilibrium is stressed, the reaction will shift, aka favor one side, to relieve that stress, reestablishing equilibrium. So Le Chatelier's principle is the guiding principle that allows us to qualitatively understand and state that a reaction at equilibrium, if stressed, will favor the left or the right side to relieve the stress in an effort to reestablish equilibrium. Another way to put this is in response to changes, the reaction shifts predictably. I'm now going to draw a table of 7 rows and 3 columns. This is going to be a little text heavy. I'll give you guys a minute or so just to draw it yourself. And we're going to be drawing a table of 7 rows and 3 columns. I've just written 7R, 3C, so you can draw it yourself. Three C. Right. Whoops, 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 whoops. Where'd it go? Oh, there it is. Okay. The column headings are as follows. If we the reaction will shift and because the system. So the column headings, you should maybe already have an idea. It should kind of read as a full run-on sentence. So notice that we says if we're going to make some changes to the reaction, and we're going to see how the reaction will shift in response and why the reaction shifts in response. First one, if we add a reactant or product, R or P to represent reactant or product, if we add a reactant or product, the system will shift away from that reactant or product. So think about how we're supposed to read it. If we add reactant product, the reaction will shift away from that reactant or product because the system consumes the excess reactant or product. So the table is meant to be read in a full run-on sentence. Let's just go over it again so you understand. If we add reactant or product, the reaction will shift away from reactant or product because the system consumes the excess reactant or product. We can also remove the reactant or product. If we remove a reactant or product, the reaction will shift towards that reactant or product because the system wants to replace what was lost. So think about what we're doing here. We are literally stressing out the reaction. It'll be on its merry way at 10:30 in the morning, and you out of nowhere say, I'm just going to add some extra reactant. I'm going to add some extra product. That's a stress. The reaction wasn't prepared for it. It's now saying, now I have to do something in response to this stressful situation. If I add a reactant or product, I'm going to shift away from that reactant or product. If I remove reactant or product, I will shift towards that reactant or product. What else can we do? We can increase the pressure of the reaction. Remember that gases are included in equilibria. Gases most notably manifest as pressure. That's how we verify the existence of gases. So we can increase the pressure. If we increase pressure, the reaction will shift towards fewer gases. And the reason it does this is that it overall reduces the total volume. This comes back to Boyle's law, P1V1 is equal to P2V2. If we increase pressure, we have to decrease volume, and to do that, we go towards fewer gases. If we decrease pressure, maybe you're kind of already able to predict this. It's just the opposite. Instead of going towards fewer gases, we'll actually be going towards more gases. Where, of course, the reason why the system does this is to increase the total volume. That's pressure. The last category is increasing temperature. If we increase temperature, the reaction will shift towards the endo direction. We know what that means from last week's topic. An endothermic reaction is one that has a positive energy associated with it. So if you increase temperature, we will favor that positive direction. The reason why it does this is that it absorbs the extra heat. Remember, what does endo mean? Endo means energy enters. In an endothermic reaction, we expect the temperature to go down. So think about it that way. If I purposefully increase the temperature, the reaction will respond to stress by trying to decrease that temperature, favoring endo. If I decrease temperature, I will in fact favor the exo direction, the negative. Where, of course, the purpose is here to produce heat. Just realized that that meeting being recorded is blocking some of the things. So, yeah. These are the guiding principles of Le Chatelier's principle. Sorry for using the same word twice. And now I have a handout that I'm going to pass out. 1 second, put it in the wrong folder. 2 of you. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Both of you. Did I give you enough copies? I did. Okay. 2. Thank you. 2, 3, 4. You guys. 1, 2, 3. And 1, 2, 3. Any extras? No, it looks like everyone got it. All right. What I've just now handed out is a typed up format of the table on my GoodNotes. This table outlines or just reiterates Le Chatelier's principle and its effects. You will not be given this chart on the exam. It is something you are expected to memorize. You will not be given this chart, this table as part of your next exam. You will need to memorize it because I will ask you in questions, based on the following stressors, predict how the reaction will shift and what direction. Let's take a look at a use case of Le Chatelier's principle. Let's understand why and how exactly Le Chatelier's principle is as useful as we hope it to be. Let's look at an application of it. Specifically, we're looking at what's known as the Haber-Bosch process. I do not expect you to memorize this process. I'm just giving you an example of how it's used in the real world. The Haber-Bosch process is as follows. It is the reaction between nitrogen and hydrogen and is the preferred industrial method to making NH3, aka ammonia. The Haber-Bosch process, like I said, I don't expect you to memorize the details of what the Haber-Bosch process is. I'm just giving you an example of it. But this is the reaction that industries use to make NH3, aka ammonia. It is the combination of nitrogen gas as well as hydrogen gas and is known to have a delta H value of negative 92.2 kilojoules per mole. The Haber-Bosch process represents one of the most synthetically useful reactions in all of chemistry. Ammonia is so easy to make, there's no point to trying to purchase it off of another supplier. Most companies are able to make it themselves because this is one of the world's most well-studied reactions due to its simplicity. Nitrogen and hydrogen exist all around us in the atmosphere. So a lot of time has been spent trying to maximize the efficiency of this reaction. There are a couple things that we can look at or identify based on this reaction that will help us identify uses of Le Chatelier's. One of the first things we hopefully notice is that the reaction is exothermic to the right. How do we know it's exo? Well, the energy value is negative. That alone tells us it's exo. But when we're dealing with a reversible reaction, one goes left and one goes right, how do I know specifically that this is exo to the right? Well, that actually just comes back to the US education system. We write and read from left to right. So this is literally read as the formation of NH3 from N2 and H2 is exothermic. In other words, if I were to give you positive 88.3, just as another example, it will be to the right, because we read from left to right, but the positive tells us this is specifically endo from left to right. The other thing we can tell from this reaction is that on the left-hand side, we have in total 4 moles of gases. Where do those 4 come from? Well, we have 1 mole of N2, and 3 moles of H2. So in total, 4 gases on the left-hand side. How do we know they're gases? Well, the state symbol tells us. On the product side, we have in total 2 moles of gases, specifically just the one gas. Based on this alone, we can say that the product side has fewer gases, the reactant side has more gases. This is all information we can very quickly glean just by looking at the reaction. How does this help these industries maximize the efficiency of the reaction? Well, let's first look at the exo. You have the handout in front of you, so you know how temperature affects it. If we want to favor the exo direction, what do? We decrease the temperature. Where is that coming from? Let's look back at the Le Chatelier's principle. It says if we decrease temperature, the reaction will shift towards the exo direction. That's what we want. We want to make NH3, so that is the exo direction to the right. So a condition that they will use is they perform this reaction at lower temperatures. Because a decrease in temperature favors the exo side. All right, that's what we can tell based off of the exo. Not useful for this conversation, but if we were to instead react this at higher temperatures, that would favor the endo direction. Which brave soul wants to tell us? Is that going to be to the left or to the right? To the right is exo. So to the left. Remember, we talked about this in thermochemistry. The negative and positive refer to direction. So if negative is to the right, positive must be to the left. This makes more reactants. Now, let me ask you, if you were on the board of trustees for this company and they come and tell you, yeah, we're making tons of reactants, are you going to be happy with that? No. Why? We're trying to make the product. We're trying to make NH3. Why are you telling me we're making more reactant? That's not productive. That's not useful. So Le Chatelier's principle has impact not only on chemical reactions, but their efficiency. If we want to make ammonia, we lower temperature. If we wanted to make the reactants, what would we do? We would increase the temperature. All right, that's based off of the exo stuff. Let's look at the gases. Looking back at Le Chatelier's principle, there is 2 conditions that affect gases. That's about pressure. Don't shout out the answer, but think deeply. You are on the board of trustees of this company, and your priority is making ammonia. That is the side with fewer gases. So what are you expecting in terms of pressure? Don't say it out loud. Just look at Le Chatelier's table. We want the fewer side. We want to favor the fewer side. To accomplish that, we will perform this reaction at higher pressures. Why? Because higher pressures favor the fewer amount of gases. This is again to the right. The last thing that this company does is, since they're a company, they're industrial, they have, they have equipment, they have money. Something else they can do, and they do, is they continually remove NH3. You see, in the experiment, yeah, this is taking place in either a flask or something, but remember, this is a big industrial reaction. So we're talking on a scale of like kilograms or tons. So we're not just working out of a simple test tube. We're working out of like one of those big old vats. It is possible through different equipment to continually remove the ammonia that's formed. Don't say anything out loud, but look back at Le Chatelier's principle. What happens if we remove a chemical? It's a second row. If we remove a reactant, if we remove a product, specifically NH3, which side do we favor? We favor that same side. Why? Because we want to replace what was lost. So by continually removing NH3, you favor the right-hand side. In other words, as I remove it, I am making more of it. These three conditions all act together to maximize the efficiency of the Haber-Bosch process. It allows us to qualitatively predict, hey, if I want to make a lot of product, what do I have to do? Well, it's exo, so I have to lower the temperature. The product side has fewer gases, so I'm going to increase the temperature, the pressure. And I'm going to continually remove the product to make more product. This simple logic is what catapulted this into being one of the most efficient reactions out there. Human beings make ammonia, NH3, better than nature ever can, because we can control these factors. And this is the utility of the Le Chatelier's principle. There is something else that these industries use. They use catalysts. Now, all you need to know about catalysts in the case of equilibrium is that they actually do not affect the equilibrium constant. Catalysts only speed up the reaction. We saw catalysts in our kinetics conversation. We talked about how they provide an alternate pathway that simply serve to speed up the reaction. Catalysts do not have anything to do with Le Chatelier's principle. They're just known in general to speed up reactions. So by throwing a catalyst at this, the reaction is even more efficient. Do we have any questions on Le Chatelier's principle or use of it in the Haber-Bosch process? Okay. With that, we will officially end module exam 4 content. This is the last topic that will be on your exam next week. Come Wednesday, we will have a focused workshop on equilibrium, just like last week's topic. It's 1:10. We're going to end lecture for today. I'll see you all at 1:30 p.m. for a wet lab in 604. By Wednesday's class, I'll also have a draft of the exam made and able to give you more information on what to expect. See you guys in about 20 minutes.